So I have these two questions. I probably should have done them before, but I think I haven't done it. They both relate to capacitors. Let me do this question first, and then I'll do the next question. Let me write down some formulas that I'd say are worth memorizing with respect to capacitors. And I guess my demonstration that they are worth memorizing is you will see me having memorized them. So I will say capacitor quote-unquote formulas. Some of them are actually definitions, and definitions I always recommend memorizing them. That's kind of the starting place. If you don't have them memorized, you should at least know where to look it up. It's like definitions of English words in an English class. If you don't have them memorized, you should at least know where to find them in a dictionary. So the first is the what I call definition of capacitance. So we use letter C for capacitance, and it's defined as a capacity to hold a charge. So it's proportional to amount of charge being held, positive or negative on either side of the capacitor. And the amount of charge you hold will be proportional to the voltage difference between the plates. So you normalize it by the amount of voltage. Then this is usually a quantity that's a constant for a given object. So that's one, and because I looked ahead to the next question, I know I need to know the energy stored in a capacitor. So I guess energy of capacitor stored in a capacitor. And I represent this in three forms. I guess I would start with the version that's the easiest to remember. It's easiest to remember because it kind of ties to this relationship for potential energy and voltage. The potential energy change is amount of charge times delta V. So because it relates to that, this version is a little bit easier to remember as Q times V, where Q and V both refer to the quantities related to the capacitor. And I left a little space up here because I remember there's a factor of 1/2. That comes from doing the integration, and if you're just relying on this, that's the factor you will forget. So it's energy stored on a capacitor. Once you have this form, it can be represented in two other forms using the definition of capacitance. It's a matter of, because Q and V are related to each other. So in this form, it makes it appear there's more unknowns than there actually are. So I can eliminate Q using imagining this one solved for Q. I can plug that in to eliminate Q. Then I get 1/2 capacitance times voltage squared. Or I can eliminate V by using this equation solved for V. Then I get 1/2, this time Q squared, divided by C. So, in terms of having things memorized, I have this memorized, because that's the definition, and I have this memorized because it's easy to memorize. And these two, I almost always derive it on the spot from what I've memorized. That's why I didn't write these two down to start with, because I don't have them memorized. I have to write it down based on other things I have memorized. So, okay, so we are being given voltage applied and how much charge it holds. So, wait, what? Sorry, that's not the voltage applied. That's the capacitance of the capacitor. Yeah, so the voltage applied, I guess I can use this. I already solved for it. So amount of charge divided by capacitance. I'll use Wolfram alpha again, just type in with all the units, and Wolfram alpha will do the unit conversion for me, although looking at it, I can see the micros will just cancel out. But it's fine. Yeah, I don't think I can really do this in my head. Can I? I mean, I can take a stab at it, like 1.1, maybe 0.8. 7. Oh, I might be doing wrong. Let me see. Let me just use the calculator. I'm just trying to do a version of mental math that's not working. Oh, actually, okay, now it should be 1.9.9 maybe. 0.999. I don't know. 3. So let me do it properly on the calculator. So Q, 2.8 microcoulomb divided by 3 microfarad. Then, yeah, 0. Oh, I'm pretty close. Yeah, I had to get it within 1% of the correct answer. I was doing 3 divided by 2.8 by mistake before. And I believe sometimes, people use letter U to use, say, micro, which isn't right because U is U. That U looking thing, that's mu. That's a Greek letter. But I believe Wolfram Alpha will probably understand this non-standard notation just because it's so common. Yeah, you can always double check that it did understand you correctly. Yeah, Wolfram Alpha will understand that. So yeah, so this is the first question. Let me look at the next question, which will again involve the some sort of capacitor, capacitance, and energy this time. So a capacitor has this much charge when connected to this much battery. So that will be the battery across the capacitor. How much energy is stored in the capacitor? So I would start with these 3 energy formulas for a capacitor and then see which one I should use. So I'm not being given the capacitance of the capacitor, but fortunately I have charge and V, and I have a formula that involves just charge and V. So I can just do the 7 times 3 and answer micro. Yeah, so I think I can just put in 21 and that should be right. Why? Oh, because factor 1/2. Yeah, that's right in the formula, but I forgot that I wrote the factor 1/2. Yeah, so yeah, just don't forget this 1/2. It comes from the fact, I guess there's 2 different ways of looking at it, which I cover in lecture. You could either look at it as what's called the self energy of the charge distribution being double counted. So you need to divide it by half to correct for the double counting. Or you can imagine charging up a capacitor from 0 charge to some amount of charge. And in imagining that charging up process, you have to use an integral. And in that integral, you get this factor of 1/2. So yeah, that's these 2 easy questions involving capacitor.